Chapter 4 is an introduction to what a chemical bond is. That's been controversial for over a century, and it's progressed through various stages of understanding. One of the first models was the ionic bonding model, and that's the one we're going to take first. And within the ionic bonding model chapter, we're going to learn how to write and name compounds. So that's what this 50 ways to name your compound extra credit is for. Okay. If the instructions give you a compound formula for that number, you write the name. And if it gives you a name, you write the formula. And I can tell if you've just looked them up on the internet because of the way they're spelled. So I suggest you do it the way you learn it in class and not the way you look it up on Google. All right. Just skip that. We're going to get to all those anyway. One way of defining a chemical bond is the attractive force between two atoms that form a unit. These interactions that occur for the ionic bond are purely electrostatic. In other words, you've got a positively charged atom and a negatively charged atom, and they attract each other simply by electrostatics. That's fairly easy to understand. But not all bonds are formed that way. Some bonds are formed by sharing electrons. When you've got an ionic bond formed, you will always see a metal and a nonmetal. So you know where those are located on the periodic table. You can tell whether you expect an ionic bond from those two. The covalent bonds are formed between two nonmetals. So say if you had carbon and oxygen, they cannot form an ionic bond. It has to be covalent. And covalent means they share electrons. So think about it this way. With our nuclear model of the atom, you've got a very dense center that's positively charged, and then you've got these electrons out here that balance that charge. Well, when two atoms approach each other, what do they see first? They see the electrons, right? The electrons interact first. Now, if they happen to be deficient in an electron, say they're missing one electron, what charge should they have? +1. They've got an excess of one positive charge because they're missing one negative. Okay, that's the way you form ions, by adding or subtracting electrons. You can't mess with the protons, or else what? You end up with a different element, right? Okay. So once you form these ions by transfer, an example of that is, say you have sodium metal, and it comes into contact with chlorine gas. Well, on the atomic level, you would see this sodium with how many electrons and protons? 11. Okay. 11 protons, 11 electrons. That's neutral. And this chlorine, you'd have to break the bond first, but if you had one chlorine atom, then you'd have 17, I believe. 17 protons and 17 electrons. Okay? This is the metal, this is the nonmetal. Metals love to give up electrons. Nonmetals love to acquire electrons. So if you transferred one electron from sodium over to chlorine, now you've got only 10. So 10 negatives and 11 positives is a +1 charge. You've added an electron here, so now you have 18. So 18 negatives and 17 positives is a negative. Okay, so there you have the attractive force between two ions. This is known, when it's the ion, it's the cation. Positively charged atoms are cations. Negatively charged ions are anions. Now for sharing electrons, for instance, if we had, let me try to be as simple. Let's take it really simply. Say hydrogen. Now hydrogen is kind of off by itself, but when hydrogen comes together, it forms a bond with another hydrogen atom. Right? It has one electron, and this hydrogen has one electron. If they're going to form a bond, I mean, how are you going to transfer an electron? Because they're both the same atom, right? Then there's no difference in electron attraction. So they just share those two electrons and form a single bond. So that's why you get H2, the diatomic element. That's a covalent bond. And there was a lot of, every once in a while, most scientists are analysts. In other words, they tear things down to see how they work. But every once in a while you get a scientist who sees the big picture and they pull all these things together into a cohesive story. Linus Pauling was one of those. He was a chemist and he wrote this book called The Nature of the Chemical Bond. And based on that book, he got a Nobel Prize for it. It was a description of everything that they knew up to that point about how the chemical bond worked. Okay, so here's your ionic bond, and it always involves a transfer of electrons. You got to move an electron from one atom, a metal, to a non-metal, and form that difference in charge. And that forms an ionic compound. The nice thing about ionic compounds is once you learned what the preferred or the indicated charge is on the cation and the anion, you can construct the simplest formula for the compound simply by balancing the charges. Right? Sodium is going to be a +1, chlorine is going to be a -1, so you always write just NaCl. That's it. That's all you need to balance and make a neutral compound. So when we form an ionic compound, you actually don't have individual sodium and chlorine ions grouped together moving around. For ionic compounds, you have a network of positive and negative charges. So if you spill salt on the table and look at it with a magnifying glass, has anybody in here ever done that? No. It's rare among students to do that. But if you look at the little pieces of salt, what shape do you see? You might even be able to see it with the naked eye. Cubes, little cubes, right? Those cubes, they're too big to be individual atoms, right? So you have a network of sodium and chloride ions stacked together. Sodium, chlorine, and then in 3 dimensions. So for an ionic compound, we write a formula, the simplest ratio of positives to negatives. So sodium chloride would be like this. Calcium chloride would be like this. Aluminum chloride would be like this. But they would be in a network. That would be the simplest expression of their association. For every 1 aluminum, you have 3 chlorines. On the other hand, covalent bonds formed by sharing form individual, discrete molecules. So like water. Water molecule is going to be like this. 2 hydrogens and 1 oxygen. And they act independently. So when you write the formula for a covalent compound, That is a molecule. Now, like I've said before, nature just does what it does, and we try to make sense of it. And one of the ways we make sense is to split it down the middle and say these are ionic and these are covalent. But the reality is, the closer those metals get to the nonmetals in the periodic table, the more covalent character that they have. So it's not completely ionic. We use ionic for metals and nonmetals simply because it's easier to produce the formula. But you have to recognize that once the bond forms, it may not be completely ionic. That is, that electron that was transferred may actually spend more time with the nonmetal and a little bit of time with the metal. So you get that continuum from 100% ionic to 100% covalent. Another concept about bonding is not all the electrons, at this point, consider this, not all the electrons that surround an atom participate in bonding. This idea came forth as what we call the valence electrons, those in the outermost energy shell, principal quantum number. So if we had something like, let's take potassium. Right? We know potassium has 19, right? And we know how to write its electronic configuration. Right? We can just whip it right off there. Six. So that's 10. We need 9 more. 3s 2. 3. Wait a minute. 1s2, 2s2. Yeah. 3. That's not 19, is it? Yeah, potassium's 19. Okay, I messed up. 2, 4, that's 10. I need 9 more. So 3s, I still got 3p, 6, then 4s, 1. That should be it. So that's 10, and that's 9. Okay, so there's your configuration. What's the highest level shell here? That one right there. Right. So it only has one valence electron. That's why when it transfers an electron, it only transfers one. That's the one that's available. These are not. This is known as valence because it can participate in bonding, and these are core. They are too tightly bound to be participate in bonding. Now, the next concept you may have gotten in biology class or anatomy and physiology called the octet rule. You ever heard of that? Way back in the dim reaches of your mind. Okay. What we're saying is, for period 2 and period 3, where you're moving through only S's and P's. We haven't introduced D's yet. For those atoms, and particularly for carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, I said fluoride and chlorine, and the metals also that are in that those periods. For period 2 and 3, we have for period 2, we have this. These are the orbitals being filled. Right? So sodium, lithium and beryllium here, and then boron, carbon, nitrogen, oxygen, fluorine, and neon here. And then when we get down to the third period, now we're talking about sodium, magnesium, and aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So there. Okay, the octet rule means these atoms, when they form bonds, they're tending toward an outer shell of 8 electrons, octet. So you see here, 2 there and 6 there, that's 8. So how do they get there? Well, potassium works pretty well with this too. Potassium would get to an octet one of 2 ways. Either you add 7 electrons, which is a tall order, or you just kick that one out. And now you're looking at this. There's your octet. So what does that octet mean for potassium plus? That means it looks like, electronically, it looks like argon. It has 18 electrons, not 19 now. It looks like argon. So they're tending toward the octet to mimic noble gases, because the noble gas has complete shell and is perfectly happy. It doesn't react with anything. So if it can do that by transferring an electron, so much the better. So it just gets rid of that electron. Now it has an outer octet. What about, let's see, potassium. What about chlorine? Right. Chlorine is 17. Right. So it's going to be 1s2, 2s2, 2p6, 3s2, and 3p5. I think. That's 10 and 7. Yeah. So how does chlorine get its octet? It accepts an electron. It fills this one to make P complete. And now it has a negative charge. And it also looks like argon, electronically speaking. All right? It's happy with its octet. Right here. Okay, ionic bonds are formed by transfer of electrons. It could be 1 electron, it could be 2. It depends how many is required. We talked about valence electrons. All valence electrons have the same principal quantum number. Now, that we've described the octet, an American chemist by the name of G.N. Lewis was working with chemical bonding, and he wanted a simplified way of expressing how the electrons in the valence shell were arranged around an atom, and then how they interacted with one another. He wanted a symbolic language. So he created what we call Lewis symbols, or I call them Lewis dot structures. Let's leave these here like that. Like that. So what we're going to do is, and let's put our, let's bring it back to neutral. So this would be 5, and this would be 1. Okay? These are the valence here, these are the valence here. So Lewis was working only with valence electrons, because it was accepted theory at that time that only the valence electrons participated in bonding. So if we draw this symbol with a Lewis in mind, it has 1 valence electron available. That would be his symbol for potassium, the neutral atom of potassium. We're only showing that 1 valence electron. Whereas chlorine would have 7. 1, 2, 3, 4, 5. Let's do like this. 5, 6, 7. Okay? So if he wanted to form a bond, he needed to complete the octet. So to complete the octet for chlorine, he would simply put this potassium here with its, I'm going to change it to an X so we know where it came from. He would just form a bond like that. Now if you count 1, 2, 3, 4, 5, 6, 7, 8. Chlorine has an octet. Or if you count potassium, well, it only has 2. That's the way it's supposed to work, but it doesn't give, it's not obvious potassium has an octet. It's underneath. Oh, I know. It works better with covalent compounds. I probably should have used a different example. So here are some examples of dot structures. Notice that in the first column, all the elements have only 1 dot. Second column, they have 2 dots, right? Because they have 2 electrons in their s orbitals. If we go to the far right-hand side, helium, of course, only has 2 because it doesn't have access to the octet. It only has 1 s access. That's only 2 electrons. But if you move down to neon and argon, then they have complete octets. They have 8 dots around them. Fluorine and chlorine, all the halogens only have 7 dots. So they need 1 more to make their octet. The chalcogens, oxygen group, they all have 6 dots, which means they need 2 more. And the pnictogens, they only have 5, so they need 3 more. The carbon group has 4, it needs 4 more. And so forth. So how about the number of valence electrons in each of the following elements? We can tell the number of valence electrons. All we have to do is look at the periodic table. Where's calcium? Excuse me, calcium. It's in the alkaline earth group. It has 2 valence electrons. All right, count from the left. 1, 2. Calcium has 2 valence electrons. How about selenium? Selenium is going to have principal quantum number 4. So you potassium, calcium, then you have to go across the 3 group, right, 3 Ds, and then you go back to the 4s, gallium, germanium, arsenic, selenium. Selenium has 4 p electrons and 2 s's. That means it has 6 valence electrons. Right, 4s2 and 4p4. Now when you write it that way, we skip the 3 Ds. They're lower energy than the 4s. So the 4s2 and the 4p4 are valence electrons. Carbon has 2s2 and 2p2. There you go, 4 valence electrons. Now the carbon group is unique in that it can get to its octet by either losing those 4 or gaining 4 more. Usually it gains 4. Okay. These are just generalizations. How are we doing on time? Okay. Time moves slower when you're hot. Representative elements in the same group have the same number of valence electrons. I think we showed that. Number of valence electrons for representative elements is the same as the Roman numeral old style group. So if you see the Roman numeral up there, 1A, 2A, 3, 4, 5, 6, 7, 8, well, they don't put A, they put 0. The valence electrons are that Roman numeral. So all the halogens are going to have that Roman numeral 7 above them. Now this doesn't work for the transitions. They're all B's. Just the Roman numeral A's. Maximum number of valence electrons for any element is 8. That's true for actually groups 2, 3, and 4. Come on, here we go. How about the Lewis symbols for oxygen? Well, which oxygen is in group 6, right? So we just say oxygen, 1, 2, 3, 4, 5, 6. Remember Hund's rule, pairing up electrons? That's why I ran around first and then I started pairing. All right, so there's oxygen. How about phosphorus? It's in nitrogen's group, it has 5, right? So phosphorus is going to be 1, 2, 3, 4, 5. And fluorine is a halogen. 1, 2, 3, 4, 5, 6, 7. Okay. Valence electron is an electron in the outermost electron shell of an atom. Yeah. The shorthand method developed by scientists is Lewis, electron dot symbols. Yeah, the full octet means stability. So that's why the noble gases don't form compounds, typically. Now, krypton and xenon, you can force them into a situation where they make compounds, but they don't normally do that. Not in nature, anyway. I mentioned this earlier. When the atom forms the octet due to a bond, it's trying to imitate the noble gas configuration. All right. So I mentioned earlier how you form an ion. I kind of got ahead of myself. You form ions by gaining or losing electrons. And then the balance tells you what the charge is. If you gain an electron, you're making it more negative. If you lose an electron, you're making it more positive. And don't mess with the protons. That only happens in nuclear reactors and atom bombs. Okay, these are just examples. I think we beat that horse enough. So, an ion formed when a potassium atom loses one electron. Give the chemical symbol for each of the following. Well, if potassium loses an electron, it's going to be 1 positive, right? So potassium would be like this. That would be the potassium cation. Sulfur would gain 2 electrons and be like that. And notice sulfur is in the chalcogens. It's an oxygen group. Oxygen would do the same thing. Selenium would do the same thing. Tellurium would do the same thing. It would gain 2 electrons in a chemical reaction. Typically. You know, as the saying goes, there are always exceptions. Very rarely do I say absolutely blah, blah, blah. Atoms can either lose or gain electrons, resulting in the formation of ions, cations, or anions. All of them. Okay. I don't think we need to beat this horse anymore. Atoms tend to gain or lose electrons until they have obtained an electron configuration, noble gas. So if we want sodium plus out of that configuration is the neutral configuration for sodium. You'd have to lose that S electron and make it look like neon in order to be positive. So that's really, that electronic configuration for the sodium plus 1 ion is not right. It's got too many electrons. You need to lose one of those electrons and make it look like neon. Gain 7 electrons would give it, oh, I see. If sodium gains 7 electrons, it'd look like argon, but it's really, really hard to stuff that many electrons into one atom. So the more likely one is just to lose one electron. Okay, so this is kind of leading up to naming compounds. There are groups of elements in here that when they acquire a charge in an ionic compound, they always acquire the same charge. The alkaline metals are always +1. The alkaline earths are always +2. Boron, aluminum, gallium, and indium are always +3. Okay. Carbon can be, it's ambidextrous. Nitrogen, go from the other side now. Fluorine and the halogens are -1 charge. Oxygen and its group are -2 charge, and the nicogens are -3 charge. Now this is for ionic compounds. You're going to see in periodic tables several charges, especially with the nonmetals. Those are not necessarily charges. We haven't talked about oxidation states yet. So the first one in that group should be the charge. You can equate that with the charge. So if chlorine has, it looks like 1, 2, 3, 4, 5 values up there, the top one should be -1. And the rest of them are oxidation states that it acquires in covalent bonding. We'll have to talk about that later. All right. Oh, we already covered these. The nonmetals have fixed charges also. Carbon can go either way. Now the concept of isoelectronic species simply means that if you have a group of atoms and ions and they all have the same electronic configuration, they're said to be isoelectronic. Iso is the Greek prefix that means the same. You know those little bugs that run around, the isopods? We call them roly-polies. You touch them and they go like that. They're called isopods because they got all these little feet and they're all the same. Pod is foot and iso is same, so they have the same foot. So, if we take, say, actually neon, 1s2, 2s2, 2p6 is the configuration for neon. So we could stick neon in there too. And all of these ions have exactly the same electronic configuration with an octet in their outermost shell. Now, isoelectronic series don't necessarily have to be imitating noble gases. Right? Under exotic conditions you can have different ions. All they have to have is the same electronic configuration. But for our purposes, we're going to keep it simple, right, at this stage, and we're going to limit our isoelectronic series to those that mimic noble gas configurations. All right, I'm not going to dwell on that one. We don't have to spend a lot of time on this one either. An alkaline metal, alkaline earth, noble gas, and halogen, so that they have the same, so that they're isoelectronic. Right? And we could do those. These all look like argon. Potassium 1+, calcium 2+, chlorine 1-, all look like argon with that configuration. So if they're in the same period, actually if they're in the same period as argon, the nonmetals work because all you have to do is add electrons to get to argon. But if you're going to go from the metals, you got to subtract electrons and work backwards. So you have to move down to the next period. So potassium and calcium would be candidates for isoelectronic with argon because they're coming in from the other side. Okay, each has 18 electrons, but they all have different protons. Okay. All right. How about magnesium? Can we write the magnesium ion? Sometimes the easiest way to do an ion is write the neutral first and then make an ion out of it. So if we got magnesium, we look up there, magnesium has 12 electrons when it's neutral. That's 10, and then 3s2. So if it's going to form, if it's going to make an octet, it's going to look like a noble gas, we've got to get rid of those two. So remove two negatives, you get two positives, and that's gone. So that would be magnesium 2+, which would be A, wouldn't it? Yeah. Okay. I mentioned this earlier. Only metals and nonmetals form ionic compounds. The metal loses or donates the electrons from its outer shell. The nonmetal accepts those electrons, and they both end up with octets, or noble gas configurations. And then, once they've reached that point, and this all happens simultaneously, as they approach one another, they feel the attraction of electrons from the metal to the nonmetal, and it transfers and the bond forms. We look at it in stages because it's easier to visualize it. But this all happens at once. And usually with a release of a whole lot of energy. If you react sodium metal with chlorine gas under a hood, pull the sash down, it'll be a very violent reaction, very exothermic. Okay, so if we look at these in terms of Lewis dot structures, here's our sodium and chlorine. Chlorine has 5 valence electrons. Sodium has 1. Sodium transfers the 1 over to chlorine, giving an octet. That leaves 1 deficient for sodium, makes it positive. So now sodium has a positive charge, chlorine has a -1 charge, and they attract. For oxygen, it needs 2 electrons. So when it forms a compound with sodium, it needs 2 sodiums, because sodium can only donate 1 electron each. So one sodium makes 1 donation, the other sodium makes the other donation. Oxygen's happy with 2 extra electrons. Now it's a 2-. Each of the sodiums are 1+. So our Na2O should be Na2O. This would be a 2-, this would be a 1+. And if you want to balance the charge, bring that down. 1 times 2-, and 2 times 1+. You're neutral. It's just simple math. Calcium and chlorine. Chlorine only needs 1 electron, but calcium has 2. So calcium can accommodate 2 chlorine atoms. That's why the simplest formula for this ionic compound is 1 calcium and 2 chlorines. Now since it's ionic, think back, it's still a network of calcium and chloride ions in this calcite. Have you ever seen a crystal of calcite? It's, what do they call it? It's I'm sorry? Yeah, calcite, it's a rhomboid. It's like this, only it's like that shape here, but you push it over from the side. I was trying to think of the proper word for that. It's a deformed rhomboid. And these are all based upon their crystal structures. Lewis structure, Now, what we draw when we do this, that's a Lewis structure for a compound. Just say again, they're always neutral. Ionic compounds are always neutral. We don't deal with electrostatics. That's physicists do that with their, I don't know, Van der Graaf generators. Have you ever seen a Van der Graaf? It's like a tall tube with a big silver ball on top. And you turn it on, and it's got a belt inside, and it picks up electrons from a discharge source in the bottom and deposits them in that dome. So if you take a grounded rod and you have an insulating glove on, and you touch it, you'll see a big blue spark jump across. When I was a kid, we took a tour to, this was in Oak Ridge, Tennessee, which was, like, it has the highest concentration of PhD chemists and physicists and engineers at any place in the country. So our public school system was top-notch. But we went on this field trip to a demonstration. They had a physics demonstration facility, and we went into this room, and the scientist had this big Van der Graaf generator. It was about this tall, had a big ball on it. So he picked out one of the girls with long blonde hair, and he said, okay, put your hands on that silver ball and don't take them off. Hold them there. So he turned it on, started building up charge. Charges like to leak from point sources. So they traveled through her hands into her hair and out to the ends of her hair, and her hair stood out like that. But she was obedient. She didn't take her hands off, because if she had, she'd have been in terrible shock. So after we all got a good laugh, they turned it off and discharged the ball, so it went back to neutral, and then she could take her hands off. Okay, so when we write a chemical formula, and this is particularly for, well, there's a good example. If we were to write this formula without the Lewis electrons, we would just write it like that. Okay? And what we're saying is, for every one sodium, there's one chlorine. We always write the cation first. All right, the metal goes first, non-metal goes second. And then if we need to change the numbers of atoms associated with each other, we use a subscript. Okay? So that's why calcium would be like this. Calcium needs 2 chlorines. Let's pick a different one. How about that sodium oxide? Sodium oxide. So we need 2 sodiums for each oxygen. Let's see. Or sodium phosphide. Now, I'm using names that we haven't learned yet, but that's what they're called. Chemical formulas for these guys. Well, barium chloride should be easy. Barium has a 2+ charge, chlorine has 1-, so we need 2 of them. Right? How about iron 3+ and oxygen 2+? Okay, iron 3+, oxygen, oops, wrong place, 2+. Now you got an odd and an even. How do you deal with that? Cross multiply. Bring this 2 over here. Bring that 3 over there. And then check yourself. 2 times 3+ is 6+, right? 3 times, oops, 2- is 6-, 0. Okay. Oh, and lead 4+ and oxygen 2-. Lead 4+ and oxygen 2-. We need 4 minuses to balance this 1. So if we have 2 of these, that gives us 4-, and those 2 together make it 0. So I think I've got it animated here. All right, there's barium chloride, iron 3 oxide, and lead 4 oxide. I mentioned this earlier. Solid ionic compounds have negative and positive ions arranged in a network to minimize their energy. Right? Remember, low energy is stability. So the lowest energy that can be obtained is the one that's going to be preferred for a compound. Now, there are situations where the lowest energy that can be obtained is not the lowest possible energy. I always use nitroglycerin as an example. When you put nitric acid and glycerol together with some sulfuric acid, and it forms nitroglycerin. Well, there's a lot of energy that goes into that to make the reaction happen, and then it goes into a dip to make the nitroglycerin. Well, there's still a lot of energy stored in that molecule. So all you need to do is look at it cross-eyed, and it'll go up the other hump and down and release all that energy. So the lowest localized energy was in that dip. That's how they make explosives. They store energy in the bonds. Now, some are less sensitive than nitroglycerin. Plastique or composition 4 is very stable. You can't set it off with a gun, a bullet, or a hammer. It takes a blasting cap. Okay. So this is what it would look like, 2D cross section or a 4D representation, 3D on the right. So you got the sodium ions, the little blue balls, and the chloride ions are the big green balls. Now, does that make any sense according to size? Look at sodium. It's got 11 protons. Chlorine starts off with 17 protons. So it's bigger to begin with, right? And then you add one more electron to chlorine, it balloons even more, and sodium shrinks because we took away one of its only valence electron. So that's why the blue looks small and the green looks big. This, in ionic compounds, this is known as a formula unit. And when you look on the side of a bottle and you see the formula for an ionic compound, it'll have FW underneath. Formula weight. In other words, what is the weight of that formula in terms of atomic mass units? Okay. So it would add up, if you had sodium chloride, it would add up 23 and 35.45. And that would be printed on the side of the bottle. They call it formula weight because it's not a molecule. Right? It's just the simplest expression of the ratio of those two ions. All right. Let's see. Now here are, we're going to go into naming now, and we're going to start naming binary compounds. That is, one metal, one nonmetal, or two nonmetals. Right, just one and one. That's a binary compound. And we need to realize that the alkaline metals are always +1, alkaline earths are always +2, aluminum, gallium are always +3, but there are transition metals in there that are fixed charge also. Zinc is always 2+, cadmium is always 2+, and silver is always +1. Okay, those are the only transition elements that have a fixed charge. The rest of them have variable charges, depending on the compound that you find them in. Okay. It says binary compounds are composed of two elements. We're going to stretch that a little bit. And that's why in your review document, If you look on one of the back pages, you're going to find a list of polyatomic ions. These are covalently bound atoms that behave as a molecular ion. So they behave as a single unit in an ionic compound. So when it says two elements, it could be two groups. And we're going to treat those, we're going to look at those naming conventions for ionic and covalent compounds. All right, so these are the rules. And these rules were developed with these two guiding principles. One, the name for a compound must be unambiguous. In other words, when you see that name of the compound, you can write the compound correctly and no other formula will suffice. It's unambiguous. You go backwards and forwards, there's only one possibility. There's no confusion. Also, we want the name to be non-redundant. For instance, if you have a metal in your compound and it only has one charge available to it, you don't put any information into that name that indicates the charge, because you know what the charge is. That would be non-redundant. Or if you put the charge in there, that would be redundant, and that's a no-no. I'll be more specific in a minute. So, type 1 compounds. Type 1s. They're always metals and non-metals. Okay? Even more specific than that. The metal always has a fixed charge. So that means only metals that are alkaline metals, alkaline earths, aluminum, gallium, zinc, cadmium, silver. Those are the only ones that fit this right here. Or if we have a polyatomic ion that has a plus charge, it's always the same. All right, now I'll mention that one in just a minute. So the metals determine the type 1, fixed charge, and then with a non-metal. And when you write the name, you just name the metal. All right, so this one would be sodium. And then you change the ending for the non-metal to IDE. Sodium chloride. And if we see that name, we can instantly write this formula. Let's see. How about this one? What's AG? Silver. All right. So this one is silver chloride. Okay. Let's take a weird one, like how about this one? Is that a type 1? Magnesium is fixed charge. It's group 2. Right? So it is a type 1. So this would be magnesium phosphide. Let's go the other direction. Let me write the name and see if you can give me the formula. How about this one? Formula. Calcium sulfide. It's a type 1, correct? Because it's second group. Okay, calcium. We know calcium is going to have a 2+ charge. How about sulfur? It's in the oxygen group. So what charge is it going to have? halogens are -1, oxygen group is -2. So this is going to be like that. So when we write the compound, we only need one of each. Okay, that's a type 1 compound. There's another one that might throw you for a loop. Hydrogen can be in the position of a metal or a nonmetal. If hydrogen is first, it's always paired with a nonmetal. Okay? If it's second, it's always paired with a metal. And if it's second, we would say, how about this one? Now, let me write the formula first. Let's do it that way. Okay? Fixed charge for aluminum, right? 3 plus. That would make this one a 1 minus to balance it. So we would name it aluminum hydride. Okay? If we had, say this one. Now hydrogen's first. So you just name it like you would a metal, right? Hydrogen chloride. Now, as it turns out, this is a gas. If you dissolve it in water, yeah.
So if you have a pair that is a non-metal that's paired with hydrogen, like that, and the hydrogen is first.
Yes.
It's a metal side of it, it's opposite.
Right. Yeah. And the name changes. We're going to look at what to do if we dissolve that in water. If we make it aqueous, then we use an acid naming convention. So we're getting there, which is not there yet. Okay, those are type 1s, where the metal has a fixed charge. It can only occupy one possible charge and no other. Type 2, let's see. Let me flip the slide here. Type 1, there's examples. A type 2 binary compound is also metal and non-metal. The difference is the metal could be one of 2 or more different charges. Now, it doesn't change its charge once it's in the compound. It's fixed. But it does have multiple charges available as it forms the compound. Are you already signed in? You missed the exam too. Are you Susan? Okay. We're into material for you're going to do a copy of this thing on the table. Yeah, I'll send you the stuff. I can't remember if it's on the white space name or if it's just a PDF file. And I use the Southern email addresses. Okay. So it won't show up on your personal email. All right. Okay, so type 2 compounds are also metal, non-metal. But these have variable charge. And because they have variable charge, in order to be unambiguous, the name has to indicate what the charge is. So let's go back to one that we looked at earlier, this one. Fe2O3. Oxygen's going to have a 2- charge, no doubt about that. So that's 6- here. This one has to be a 6+ to balance it. So what charge on each one of the irons would do that? A 3+, right? 3+ times 2 is a 6+. So this would be a 3+. You have to deduce the charge on the metal first before you can name it. That's what I'm doing. It has to be neutral. So a total of 6+ is distributed between 2 irons. So each one is 3+. Now that we know what the charge is, we can say iron, and then the charge with a Roman numeral, and then oxide. Okay, that would be naming convention for type 2 compounds. How about, let's see. How about this one? Remember what Cu is? Copper. Okay? So, you know that it's not a fixed charge, because it's a transition metal and it's not one of those 3 that has a fixed charge. So we have to deduce the charge. We know that oxygen is always 2-. That means one of these has to be a 2+. Okay? So we just say copper. Put the charge, oxide. Okay? Let's see, what if I give you how about this one? No, that wouldn't work. Scratch that. Let's see. How about this one? That. And name that one. Right? What's the charge on this? This has to be a -1. Right? So that means there are 3 minuses that have to be made up with 1 chromium and 3+. So now we can say chromium 3. All right. Okay. Let's see. I think we've got some examples here. Okay. All right. I guess this is as good a time as any to introduce polyatomic ions. So polyatomic ions, all of them, the way that table is set up, it's kind of small print up there, but you've got a copy at the end of your review document. It's set up with exactly the same polyatomics on the left and the right. The ones on the left are sorted by name of the compound. So acetate is the first one. And the right-hand one is sorted by formulas. So arsenic is the first one. Arsenic, arsenite. These names for the polyatomic ions are fixed. When you put them into the name of a compound, nothing changes. Right? And they have a fixed charge. And all of them in that chart are negative ions. They're anions, except for one. There's one cation that's a polyatomic. Ammonium. The rest of them are negatives. So that means this one could take the place of a metal in the name. It would be over here, right? Because it's a fixed charge. It would be a type 1 compound. But if you have an anion in a compound, like chloride, you have that in a compound, say with potassium, right, with +1, then you'd only have 1 and 1. This would be a type 1 compound because the metal is fixed. But instead of that, suppose we used, this one, Fe, and say it's a 2+. Okay? How many of these negatives would you need to balance that 2+? Because polyatomic ions are covalently bound groups, and the charge is distributed over the entire group. It's not localized on an atom. So if you need more than one of them, you have to use a parentheses. We need 2 of those negatives to balance that 2 positive. In this case, we would say iron 2 chlorate. Now, you don't have to memorize these. That's why I give them to you in that table. Just know how to use them. There are ways to rationalize several of them that are in homologous series so that you really, if you wanted to memorize them, you wouldn't have to memorize that many. Right? They follow a pattern. For instance, this one that I just put up there, the chlorate. The chlorate is ClO3 minus. That's the chlorate ion. If you take away one of those oxygens, you still have a negative charge. This is chloride. If you take away another one, we don't have any more suffixes, we need a prefix now. So we're going to stick a hypo in front of it, like underneath chloride. And similarly, if we add one on top, we need a prefix per chloride. So there you have a sequence, and if you change this to bromine, it would be bromate, bromide, hypobromite, perbromide. Right? Change it to another halogen. If it was iodine, it would be iodate, iodide, hypoiodide, and periodate. So you can get 12 of them done just like that. Okay. That's a type 2 compound. And we can substitute, say if we wanted a type 1 with ammonium. So if we did like this, and put an ammonium here, it's a +1 charge, -1 charge. It would just be ammonium chloride. Okay? Farmers know what that is. It's a nitrogen fertilizer. Or We could put another polyatomic in here for the anion. Say NO3. That's a minus, this is a plus, so they're balanced, 1 to 1. Ammonium nitrate. And every car bomber knows ammonium nitrate. You just mix 6% fuel oil with it, put a stick of dynamite in there, and you got a nice little bomb. Okay, that's why the federal government controls access to ammonium nitrate. If you're not a farmer, if you're not a licensed producer needing ammonium nitrate for your crops, you can't buy very much of it. You could buy enough for your garden. You can go down to Walmart and buy a bag, but you can't buy barrels of it. Oh, it depends on how big you want it to be. You could blow up a car with like a 55-gallon drum and then 6% fuel oil. In fact, the mining industry buys ANFO, ammonium nitrate fuel oil, ANFO. It's already in the bag, pre-mixed, so that they can open it up and they can drill holes and they put a stick of dynamite at the bottom and then ANFO on top of it and then set it off. And it produces a nice big explosion. Cracks the rock open and then they bring in the front loaders. Off you go. Okay, so this is a case where you have two polyatomic ions, but they fit the type 1 convention. If we had a polyatomic anion over here, like I think I showed you before, and you put a metal in there that has multiple possible charges, then you would have to say what the charge is on the metal. You're going to see those later when we get to acids. Okay, here's examples. Hydroxide is a polyatomic ion. It's OH minus. So don't get that one confused with H minus. This is hydride. This is hydroxide. Okay. NO3 minus is nitrate, SO42 minus is sulfate. We're still just balancing charges. The only difference is when you have a polyatomic ion, you cannot break it up. You can't change the subscripts. It has a fixed charge, and if you need more than one of them, you have to use parentheses and a subscript. Okay, type 3 compounds. Last one. These are non-metal. So the type 3 compounds are formed between atoms on the right-hand side of the periodic table. And because of that, they do not form ionic bonds. They form covalent bonds. The problem with that for our naming convention is these we just balance the charges. But over here we don't have charges, so we can't balance charges. We need to modify the convention. We're gonna work off of these and modify them for this one. So we're going to start with the first one in the group is the more metallic. So it would be more to the left and below. If you have two of them, comparing them like carbon and oxygen, if they're coming together, carbon comes first because it's to the left. Or phosphorus and chlorine. Phosphorus would come first. Chlorine would come next. That convention works in most cases. So since we don't have charges to balance, we actually in the name say how many of each atoms are in the formula or in the molecule. Okay? So if we had, say, how about this one? if we had this one nitrogen and one oxygen, then we would say, no, you wouldn't balance any charges. There are no charges here. Right? These are both nonmetals. So to name it, we say nitrogen, and then we say how many oxygens? Monoxide. Now, we do only have one nitrogen, but by convention, we don't put a mono in front of it. We only put monos for the second member. Now, if there are two nitrogens, say we had, let's change it a little bit. Say we had two nitrogens, dinitrogen, like that. Then we would say dinitrogen, and then what the prefix for 5. The Greek prefix is penta. And to make it flow easier, we drop the A and just keep the O. Now, I think there's a slide on the Greek prefixes in here. Yeah, there it is. You only have to learn through 10. All right, so 1 is mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Just memorize those. They go on a lot bigger than that, but this is as far as we're going. Okay, everybody's heard about carbon dioxide, right? That's the formula for carbon dioxide. Carbon, 1 carbon, and 2 oxygens, dioxide. And we do keep the convention of changing the ending to IDE. Okay? Sulfur hexafluoride, 1 sulfur. Nitrogen tetroxide, dinitrogen testoxide, 2 nitrogens, 4 oxygens. In many respects, the type 3 compounds are the easiest ones to deal with because you don't have to calculate anything. Right? You just count up the number of atoms if you're going to name it. Now, if we go back the other direction and say, like diphosphorus, pentoxide, right, we would have 2 phosphorus and 5 oxygens. Okay. So here's your decision tree. So you've got a binary compound. You got 2 elements, or you got 1 or 2 polyatomic ions. Just learn to recognize them. Study that chart. Then you've got to ask the next question is there a metal involved? Or is there a polyatomic that's assuming the position of the metal? Right? And the only one that can do that is ammonium. Yeah. So when you look at the metal then, you ask yourself, is that metal a fixed charge? So you look back to the periodic table and say, did it come from those places where we have fixed charges? If it did, then you got a type 1 compound. And you name it with that convention. If it comes from transition metals or over a little bit to the right, like tin, antimony, lead, bismuth, those are going to have multiple possible charges. Then it's a type 2 compound, and you have to say what the charge is. So you can't write the compound unless you can't name it unless you know what the charge is. And if you have the name, then you got to figure out what the charge is in order to write the name correctly. So that's your decision tree. Here we include polyatomics. I've already covered those. Now for acid convention. Let's see if I can do it over here and leave that alone. Acids. The thing about acids was there were a number of mineral acids that had been isolated and were used extensively by alchemists through the Dark Ages. And they had their naming convention. So what the IUPAC committee had to do, International Union of Pure and Applied Chemistry, the naming convention committee, subcommittee of that group, had to do was take those grandfathered in names and try to make sense of them in such a way that we could name more acids along those lines and be consistent with unambiguous and non-redundant. So that's why the conventions for acids are, at first glance, are a little bit wonky. First thing you'll notice when you have an acid, if you want to name it an acid, it has to be in aqueous solution, right? If it's HCl, here, say if it's HCl like this, you name it like that, type 1 convention, hydrogen chloride. But if it's like this, then you got to name it like an acid. Okay? The other thing you'll notice about acids is they always start with at least one hydrogen and then the rest of the molecule. So here we have one hydrogen and the rest. What if we had like this one? Now we've got an acid with a polyatomic, right? And there are rules for that. Or if we have two hydrogens and another polyatomic, or three hydrogens and a different polyatomic. Or if we have this one, right, formed from our perchlorate anion, a polyatomic ion. These are all acids. They start with hydrogens. Now, here's one that has a hydrogen in the beginning, and more hydrogens in the rest of the molecule. This is the one, this is the acidic hydrogen, we say. It's the one that dissociates from the molecule in aqueous solution, that makes it acidic. But those hydrogens are locked in place. They cannot move away from the molecule. They're very tightly bound. So the only one that is acidic is this one. Okay? In case you see multiple hydrogens, if there's one in the front, then they're implying acid. Okay. Now what happens when the molecule, this generic molecule, say we have H and then some other part of the molecule, like that. What happens is the hydrogen dissociates from it and leaves behind, right? It leaves its electron behind with the rest of the molecule. Okay. Now that's not really what happens, but it works for now. So if necessary, I'll tell you what the real chemistry is later. So the first rule, of course, is does it lead off with at least one hydrogen? Second rule is it in aqueous solution? Then you know you've got an acid. Then you look for this A part of the molecule, and you look for oxygens. Is there an oxygen in that part of the molecule? Here, no oxygens. This one has no oxygens. These all have oxygens, right? These have oxygens. So they follow a different naming convention. The ones without oxygen, and I'm going to have to erase them. I'll write them again if I need it. The ones without oxygen start with, their name starts with hydro. Then we take this part of the molecule and ides become X. If this is hydrogen chloride, chloride becomes chloric. So hydrochloric acid is the name of that one. An example here of the polyatomic HCN. Okay? There's no oxygen there. So we start the name with hydro. We say hydro. And then we look to the non-acid name. This would be hydrogen cyanide. Cn minus is the polyatomic ion cyanide. So this would be hydrogen cyanide. So cyanide becomes cyanic, hydrocyanic acid. Okay? And the last one is a good example. This one, this would be hydrogen sulfide. So sulfide becomes not sulfic. It doesn't sound right, so we say sulfuric. This would be hydro sulfuric acid. All because there's no oxygen. Now, if there is oxygen in the molecule, you don't say hydro. You go immediately to the A part of the molecule. So HNO3, as this part is the nitrate. And 8s become X. So this would be nitric acid. Okay? Suppose in the homologous series we have this one, HNO2. Okay? NO2 is a polyatomic ion which is nitrite, not nitrate. So ites become us. So this would be nitrous acid. Okay? That one I did before, C2H3O2. C2H3O2 is the acetate polyatomic ion. 8s become X. So it's acetic acid. And everybody knows acetic acid. If you've ever put vinegar and oil on your salad, 5% acetic acid is vinegar. Okay. Okay, so here are some where we do ite to us. So SO4 is sulfate, so it's sulfuric acid. SO3 is sulfite, so it's sulfurous acid. And here's your decision tree. All right. Are we getting close to the end? Oh, no, we have to balance equations, don't we? Are we going to do that now or do that later? No, we must do that later. I'm sorry? No. Let me see. We're going to do that in chapter 6. Yeah, that's chapter 6. Sorry, I'm getting ahead of myself. Okay, so which one of these is named incorrectly? Well, A says potassium nitrate. Is that right? Is that a type 1, type 2, or type 3? Well, first of all, it's a metal nonmetal, correct? Or a metal polyatomic ion. So it's either a 1 or a 2. So then you look, see where potassium is. Potassium is an alkali metal. It's a fixed charge. It's a type 1 compound. So potassium, NO3 is nitrate. That's correctly written. How about titanium 2 oxide? Well, it's either a 1 or a 2. Titanium is a transition metal that has multiple possible charges. So, with 2 oxygens, with 2 minus each, that means 4 minus. This should be a 4 plus. Is it written that way? No. Titanium 2 is wrong. So, that one's wrong. How about SnO4 taken 4 times? Sn is 10, right? It has multiple charges possible, so it's a type 2. Hydroxide is a -1 charge, so 4 times a -1 is 4 minuses. That means that 110 has to be a 4 plus. That's written correctly. 10 for hydroxide. Back when I first took chemistry, this wasn't the convention. We had to learn suffixes to various things like stannous versus stannic. And you had to know the charges that were associated with each one. Because stannic and stannous is one way, and let's see, plumbic and plumbus is another way. Right, so it was a mess. So I'm glad they fixed it. How about the next one? PBr5, type 1, type 2, type 3. Is P a metal? Where's it located? It's up there with nitrogen. It's a nonmetal, right? So that's a type 3 compound. So all we have to do is say, how many are there? There's 1 phosphorus, so we just lead off with phosphorus, and 5 bromides, pentabromide. That's written correctly. How about CH203? Recognizing polyatomics is a necessary skill. One of the skills for recognizing polyatomics, most of the polyatomics have oxygen in them. So if you have 3 atoms or 3 elements in your compound and one of them is oxygen, be suspicious. Look for a polyatomic. So CrO4 is chromate, right, with a 2- charge. Right? Look in your table and say, okay, it's a 2- charge. Calcium is always a 2+ charge. It's a type 1 compound. Calcium chromate is unambiguous and non-redundant. If we put Ca parentheses 2 chromate, that would be redundant because calcium can only have a 2+ charge. And that would be a wrong answer too. Okay. So I mentioned earlier that these polyatomics, they have charges on them, but the polyatomic itself is covalently bound, which means the binding between the atoms is extremely strong, and it distributes the charge over the entire group. So OH would be, the minus wouldn't be on the oxygen or the hydrogen, it'd be on the whole thing. OH minus for hydroxide. I mentioned this earlier. Most polyatomic ions have a negative charge except for ammonium and one that we didn't mention yet, hydronium. We'll get to hydronium later, I think, when we talk about acids and bases in earnest. Don't we get to that sometime? Chemical reactions maybe. Well, if we don't worry about it, because this is a survey course. This is an introductory course, so if that's the case, if we don't need it, then we won't talk about it later. Most of them contain oxygen. with the exception of ammonium and cyanide, for instance. Hydroxide ends in IDE, cyanide ends in IDE. The rest of them are either ates or ites, with some of them with prefixes. Let's see. Okay, that number 4 is talking about the homologous series I put up on the board with the chlorine and the oxygens. We had a difference of 1 oxygen each as we moved through the series, but the charge never changed. It was always a -1. Now, if the series has the polyatomic ions have hydrogen attached to them, say we have phosphate. Right, there's the phosphate ion. If we add a hydrogen to it, now in this case, the hydrogen's going to suck up one of those negatives. We consider the hydrogen as a positive. So the positive is going to neutralize one of those. This is phosphate. And now this is 2- with a, HPO4, 2-. This is hydrogen phosphate. If we add another hydrogen, it's going to suck up another one of those. So H2PO4 is 1-. This is dihydrogen phosphate. And then if we add all 3 of them back, it's neutral, and as long as it's in aqueous solution, this is phosphoric acid. Anybody got farmers in the family? No? Okay. If you drive by a farm and you see a rusty metal gate, then the rust, of course, is going to be kind of reddish. If you come back by it later and it's kind of a greenish color, that means the farmer has gone out there and painted that rust with phosphoric acid. And phosphoric acid converts iron 3 oxide into iron 3 phosphate. And the reason you do that is because of the density of the two. Iron 3 phosphate is about the same density as the metal. Iron 3 oxide is much less dense. So that's why if you see an old car or tractor out in the field and you see rust, it's been there for a while, you see it's kind of flaking like that. It flakes because the rust is less dense. So it expands and it pushes away and exposes more metal underneath. So that's why anything made of iron left to the environment like that, if it's not stainless steel, will eventually rust down to nothing. So the farmer paints his gate with phosphoric acid and makes iron phosphate. And then, now that it's the same density as the metal, he can paint over it and seal it in. And it won't break through the paint and allow water to get in and start to rust again. There was a name for that product and I can't remember it now. But you want to be careful when you're handling it because it's very concentrated. Now this in itself is a weak acid. But if it's very concentrated, it can still do damage. Okay, polyatomic ion is there. Let's see. Right. The polyatomic ions cannot be changed. Right. They are fixed in composition and charge. So the only way to deal with putting more of them into a formula is with parentheses and subscripts. All right. That one's written correctly. It should be titanium 4 oxide. I'm moving on along here because I know if you're like me, you're about to burn up. Or you have a long time ago. How about the correct chemical formula for ammonium and carbonate? So, ammonium is like this, and carbonate is another polyatomic ion like that. Right? So now we can balance the charges because these are bona fide ions, cation, anion. We need 2 pluses to match that 2 minus. So you just put a 2 subscript, and C is our answer. Okay, this is the last one, I'm pretty sure. I added this one. I don't think this is in your textbook. Waters of hydration. There are many salts, and by that I mean ionic compounds with metals and nonmetals. Many of these salts, when you dry them down, if you dry them at, say, 105 degrees Celsius, just above the boiling point of water, then they look dry, but they have embedded in them water molecules in the crystal structure. Those are waters of hydration. The only way to get them out is to heat it more, say between 150 and about 180 degrees. Then you can drive that water off and get what we call anhydrous compounds. Okay? So if you do have waters associated with the formula, you write the formula of the salt first, and then you put a dot and how many waters there are. So for instance, if I had copper 2 sulfate, it will have 5 water molecules for every formula unit in that crystal structure. Or if I have gypsum. Everybody knows gypsum board in your houses. You don't know about gypsum board? Calcium sulfate dihydrate. That's gypsum. They squeeze it between 2 sheets of paper and seal it on the ends, and then the builders go in and slap those up on the wall, on your framing. And that's what your walls are made of. It's gypsum. Gypsum is calcium sulfate with 2 waters. Okay? Let's see. Laxatives, right? Magnesium sulfate. Has 7 waters. Okay? And there are other examples. But that's the way you write them. And when you name them, you name the compound just like you would any other way. And then after that, you say Greek prefix hydrate, dihydrate, pentahydrate, heptahydrate. So our example here is zinc sulfate. And zinc is fixed charge, right? So we just say zinc sulfate. And it happens to have 7 waters attached to it. So it's zinc sulfate heptahydrate. All right. That's the last of the naming conventions, I'm pretty sure. Well, we have questions. If you don't mind, I'm going to skip these. I'll just leave them up there long enough to be recorded.